Hello everyone, my name is Zhishen Yang from Tokyo Institute of Technology.
Hi, my name is Toshio Hirasawa from Tokyo Metropolitan University.
Today I'm going to present our system in this year's Video Guided Machine Translation Challenge. It is joint work with Professor Komachi and Professor Okazaki. Video Guided Machine Translation aims to translate video description from source language to target language. This task engages with multiple modalities, such as text in the video descriptions, video frames, etc. The challenges presented in front of us are twofold. The first challenge is which types of video features to extract. Many types of features we can extract from a video. Features from actions, visual objects, and visual scenes. We expected to use informative and high-quality features from video to guide the translation. The other challenge we are facing is to integrate multimodal features into the translation process. We need to have a model that can do this integration. The textual feature is mandatory in this video-guided machine translation challenge. Our strategies in tackling this task focus on obtaining informative and high-quality features from videos, together with using a model that is capable of integrating multimodal features in the translation process. Here, we list the three core ideas. The first is adding positional information into video representations to make use of the order information from videos. Second is keyframes in videos often contain entire images, which helps in extracting high-quality features from videos. The third is video description often involves visual objects, visual scenes, and actions appear in the video frames. We've classified two types of features that can obtain from videos: action features and appearance features. Providing these two types of features to the model is which our expectation of disambiguating and as well as making translation more precisely. We employ a bidirectional GRU model with a hierarchical attention as a baseline. That is a well-known model for the image caption translation. The model first encodes text input with a GRU encoder, video input with a video encoder. The encoded representations are then fed into the decoder with hierarchical attention. In this attention, the model first computes two context vectors over text representations and the video representations separately. The model then weighted sums the context vectors to obtain the final context vector. However, this model has one critical problem. It cannot leverage all the information from videos. To address the problem mentioned before, we employ positional encoding for the video representations. The positional encoding here is the same as in the transformer. Technically, we inject a positional encoding into video representations right after the video encoding. In the figure on the right side, we highlight the positional encoding as a green box with a bold line. We segment the video based on keyframes, and each segment contains a keyframe and 31 consecutive frames after it. We then feed the video segment list to video encoder to obtain the action feature matrix. Each feature vector in the matrix is in chronological order of appearance of its keyframe. Video description often describes objects and things in the video frames. As we talked in the core idea section, two types of appearance features we would like to obtain from videos: object features and scene features. Here, we also use the keyframe as input to imagery encoder. Integrating multiple features is another challenge. In our system, we employ a simple strategy to assemble the models to train on different types of features. At inference time, we computed the output distribution of each model, then and average them. We then select the token with the highest likelihood. Here is our implementation details. Our model has embedding of 1024, hidden state of 512. We'll apply word level tokenization for English and character level tokenization for Chinese. The vocabulary contains tokens that occur at least 5 times in the training data. For video and imagery encoders, we'll list implementation details over here. This table shows the overall performances of the models we trained with different types of features and text-only baseline. We can observe both positional encoding and keyframe extraction helps improving model performances. By encoding positional information, comparing the model 3 with the model 2, we can see performance improvements from the table. Comparing model 4 to model 3, using keyframe-based action features first improves the model by another 0.14. Our final summation is an ensemble of the model 4, 5, and 6. The ablation study is to show how useful the ensemble models trained on different types of features are. Comparing the first row to the last rows, the last two rows, an ensemble of different models brings the race in the blue score. These results show incorporating multiple features to improving translation quality. This table shows a translation example. We can see only our system with ensemble code correctly translates the group people as a swimming athlete in Chinese. This demonstrated the model successfully took the appearance feature into the translation process. We also can see their actions translated as underwater downstroke in Chinese. It is another good example of the system took advantage of action features. Here are some takeaway messages in our conclusion. We achieved the first place in the Video Guided Machine Translation Challenge 2020. In our proposed system, the keyframe-based video feature extraction, together with positional encoding, jointly improved the translation quality. We also demonstrated that the ensemble of multiple models trained on different types of features brought further performance improvements. Thank you for listening.
This is Zhi Yongwu from the University of Hong Kong. I will present the second place solution for the VMT challenge. I changed the title a bit because after the challenge is over, I made some modification to our system and obtained an even higher performance. This talk will be about the new system. We have seen rapid progress in multimodal neural machine translation, especially in image-guided neural machine translation. Researchers have explored many different models and architecture to solve image-guided NMT. The similar task, video-guided NMT, however, receives much less attention. The major bottleneck that hinders the development of VGT is the scarcity of dataset. Luckily, recent efforts like Vertex and How-To have started to alleviate this bottleneck. But still, an effective solution is missing. As we can see from here, these two tasks share a lot of similarities. Thus, most image-guided MMT techniques or models can be directly applied on visual-guided NMT or VGT. And however, they also differ in the following aspects that make the research on VGT non-trivial. The first one is that a video can be regarded as a series of closely related images and may convey much more information than the input sentence and one single image. These rich visual features, if not used carefully, can introduce noise and harm the translation. And second, video augmented natural language processing tasks are generally more challenging than their image augmented counterparts because the network need to model and aggregate the spatial temporal information in videos. And in our submission, we propose two methods, VGT shallow and VGT deep, that achieved the second place in the challenge, and furthermore, we made it to the third place in terms of single model performance. The proposed VGT shallow adopt the encoder-decoder based transformer architecture at the backbone, and we follow the common practice to extract video features and text representations separately using a pre-trained video encoder and a trained from scratch text encoder. These representations are then fast using a reconstruction trick and other operations shown in the gray box here. And the visual reconstruction module here is basically a multi-head server attention layer. We use the pre-extracted video feature to select relevant information from the encoder's output and construct a pseudo-visual representation. After that, we, like many other works, use attention and weighted sum to fast two modalities. The output is then fed into the transformer's decoder for translation. And inspired by recent success in multimodal pre-training like ViewBERT, we further extend VGT shallow by replacing the vanilla text-only transformer encoder with a multimodal encoder as shown here. The intuition here is to learn a deeply fast yet better multimodal representation for the decoder. And we denote the second model as VGT deep. Basically, in each layer of the multimodal encoder, we append a previous mentioned multimodal function component, which is the gray box here. We append it on top of the original transformer's multi-head attention sublayer and feed-forward sublayer. Here is the result of our system. We first noticed that the text-only transformer significantly outperformed previous LSTM-based models, but this does not mean that transformer should be the one-size-fits-all backbone model for VGT. Tussaud and others show that with careful design and training, a GRU-based model can achieve a 35-point-something blue score. And by assembling 9 models trained with different video features, they further boost the performance to 36 something. And for our model, we see that VGT shallow, the base version, has clearly outperformed the text-only transformer with the same model size. And by only introduced 2.6 million parameters, VGT shallow has achieved a more than 1 point improvement. The training and inference time is basically the same as the text-only transformer, demonstrating our method's effectiveness and efficiency. And while for a smaller model, VGT shallow smaller version, the performance is even higher. And one possible reason is that the sentences in vtext are relatively simple and short. We noticed that the vtext dataset has 40 words for sentences on average, such that a small model might work well while a huge model has the risk of overfitting or does not have enough training data to converge. To verify this hypothesis, we conduct an experiment using VGT, the big version, which have more than 200 million parameters, and the poor performance confirm our hypothesis above. To our surprise, the VGT deep method, in which we increase the depth of the network and encourage early and deep fusion of two modalities, generally performs worse than VGT shallow. We speculate that the reason would be if we fuse two modality earlier or inside the text encoder, it might hurt the textual representation and result in a bad translation quality. We also perform an ablation test where we evaluate the effectiveness of the proposed visual reconstruction module, which is in the red box here, and we remove it from the VGT shallow pipeline. After the removal, we observe a clear performance drop from 36 to 35, and this suggests that with this reconstruction tree, we can effectively utilize visual features while reduce the risk of introducing extra noise. Thank you for your time, and if you have further questions regarding our submission, please leave a question at the Q&A session.
Hi everyone, my name is Yuqing Song. I will present our work, Enhancing Neural Machine Translation with Multimodal Rewards. This is joint work with Shizhe Chen and Qin Jin. We are from Renmin University of China. This is the outline of our presentation. The common visual world has been widely used to bridge the semantic gap in cross-lingual communications. As shown in this figure, the word puppy has various expressions in different languages, but they have the same visual representation all around the world. Therefore, many works have explored bilingual lexicon mapping via the common image or video. Naturally, people are wondering if the visual context can help more complex but universal sentence-level cross-lingual translation. The video-guided machine translation task, aka VMT, is proposed to exploring enhancing neural machine translation system with the video contexts. Compared to the traditional machine translation task, there is a relevant video accompanied with the source sentence in VMT. The video context is expected to help translate better. Previous methods usually take the video context as an additional input with the source sentence, such as the doubly attentive translator, which attends to both source words and video features when generating the translation. We call such models as the input-side VMT model. It can benefit to disambiguate source words and make the translation model more robust to noise. The improvement is significant, especially when the source sentences are blanked out. However, when the source sentences are clean, such input-side model improves slightly to the text-purely model. Therefore, in this work, we explore to take the visual context as an additional objective to correct visually discrepant translations and generally make the learned language embeddings more visually grounded. We call it as the objective-side VMT model. Specifically, we improved the VMT model by fine-tuning it with multimodal rewards in reinforcement learning framework. We use a transformer as our VMT baseline. It consists of a source sentence encoder and a target sentence decoder. Both the encoder and decoder contain 6 stacked layers. Each layer contains multi-height attention sublayer and fully connected feed-forward sublayer. The residue connection with the layer normalization is employed to follow each sublayer. To ensure the generated translation satisfies semantic consistency with both the source language sentence and the video content, we propose to further enhance the transformer baseline with multimodal rewards in the reinforcement learning framework. We employ a video sentence matching model to provide video reward for generated translations. We divide the video into non-overlapping segments. and extract segment-level features with pre-trained IRCSN and ResNext. Then we encode the sequence dependencies of video sequence and sentence, and embed them into a common embedding space to compute their semantic similarities. After training, the visual reward of generated translation S can be computed as follows. To avoid the translation only satisfying the video content but not in accord with the source sentence, we further combine the visual reward with textual semantic reward, which is calculated by blue metric. This is the whole framework of our objective-side VMT model. We use the vertex dataset for the VMT task. To decrease the noise, we filter misaligned pairs with Jazz++. There are about 1 in 6 parallel pairs are filtered before training. In our final submission, we enlarge the training site with back translation. We use the BPE algorithm to make vocabularies for both source and target languages. This table shows our experimental results. We can see enhancing the AMT model with visual reward alone improved the baseline by 1 point blue force score. Combining the visual reward with the textual semantic reward achieves additional gain to the VMT model. The last 3 rows show the performances with training site enlarged by back translation. In our final submission, we assemble 2 models with different runs and achieve 35.28 blue force score on the testing side. In summary, we propose an objective-side VMT model by enhancing neural machine translation with multimodal rewards. The VMT model can improve state-of-the-art NMT baseline by more than 1 point blue force score with clean source synthesis. Our VMT model ranks the 3rd place at the Vertex VMT Challenge Leaderboard 2020. That's all. Thank you. If you have any questions, please feel free to contact with us.